All right, in the last video, we actually looked at this concept of a charge moving through a uniform magnetic field and equating that charge to a centripetal force, or creating that, magnetic force to a centripetal force. And this really actually does have a lot of practical applications, because if we were to shoot a charged particle, here in this case it's an electron, but if we were to shoot a charged particle of unknown mass, just by the path that it follows, we could compare relative masses. This is actually how we can identify different types of ions and things from chemicals. And so there's a lot of practical applications of this idea. Now, I'm going to kind of use this idea in conjunction with something else, okay? So we're going to use the force magnetic in conjunction with the force electric, okay? So let's say, I'm just going to kind of redraw my picture here. Let's say I have this uniform magnetic field again, and we have an electron that wants to fly down, or we'll just say a charged particle in general, wants to fly into this uniform magnetic field. Well, as we did in the last video, we know that it would arc in this direction because of our right-hand rule and the force being exerted on it in this direction. So let's go ahead and look at this idea of using an electric field in order to affect the motion of this particle, right? So let's say we wanted the particle, instead of arcing like this, we wanted it to fly straight through. So as it enters here, it's going to want to curve in this direction. So there's going to be a force to the left, all right, that is going to be a magnetic force. And in order for it not to turn or accelerate, then we would have to have our sum of all forces be equal to 0, or it be in equilibrium. So could we set up an electric field such that it would balance out, the force on the charge would balance out this magnetic force? So what we want to do is we want to have our force magnetic be equal to our force electric, okay? So if this charge flies in here, I want it to be attracted to this side. So I'm going to set up an electric field where I have a positive side over here and a negative side over here. So if I were to draw the electric field lines, remember electric field lines point from positive and negative, I want an electric field going in this direction, crisscrossing my magnetic field. So these are electric field lines, these are magnetic field lines. Right? Now, is there some way we could calculate the magnitude of this field? The answer is yes. So what we would have to do is set these equal to each other. So remember that QVB is electrical, or magnetic force, and electrical force in relation to an electric field and energy, or an electric field and a charge, is that force over charge is what gives us electric field. Remember that it's newtons over coulombs for electric field as a unit. And so if we solve this for force, right, we'll just multiply by Q over here. And so I would say I want the electric force to be equal to this, so I actually get that the charge times the velocity times the magnetic field would have to be equal to the electric field times the charge for the electron to fly straight through that field and not turn. Right? So let's kind of solve this a little bit. So the Q's go away. And we can see that the velocity that the charge would travel would simply be a ratio of the strength of the electric field to the magnetic field. This is sort of an important concept to remember and can be easily applicable on a lot of multiple choice questions and also free response style questions.